yesterday's thing still open? Okay. Same file and then one extra file. So this file is still there somewhere, right? I will later open this file as well. So I'll just save it in document. Sorry. It is there. This is the next one. And can you open that?
This one.
No. First, I'll start with this one. Can you open that journal? How do I make this?
Full screen.
No, not full screen. I just want to make this a little smaller.
You can
Zoom out. Are you sharing the correct one? No, I don't. Is it the correct one? Okay, yeah. Can you remove that tiny thing from here? Yeah. Okay, so let us start. So yesterday, let me here. So yesterday we saw this perceptron algorithm, right? So which essentially you are in this setting where your data was, so your data was basically in two types. So they were positive and negative data points. So all these data points were represented as vectors in some vector space, right? And they were linearly separable, which is to say there was a hyperplane which would separate the positives from the negatives. And if that was the case, then you could find there was an algorithm which is this perceptron algorithm which would find some hyperplane to separate these things, right. So today we are going to go into the case of when first of all we want to find maybe a better hyperplane as compared to a worse hyperplane. Like there are many different choices possible, so which one should we find? And then second, maybe we want to also handle some errors and things like that, right. And lastly, we will sort of also try to handle things when they are not directly linearly separable. Right. I mean, we saw that last thing yesterday, as in we saw that things have to be projected into a higher dimension, so that they may become linearly separable. So we'll just see how this thing is formally done essentially. So the first thing we will start off with this notion of margin. So if you look at the figure that we have here, so you have these two positive and negative data points. So you can find this separator at the top, right, or you can find this other separator. So both of these are valid linear separators, but for this separator the margin is smaller, as in if you look at the positive point that is closest to this hyperplane and the negative point that is closest to the hyperplane, right. So this distance between the closest point and the hyperplane is small as compared to this, right. So in some sense what we would like to do is find hyperplanes which have wider margins, right, because in the future new data that you could see, they will have sort of more room, so a new data point could appear somewhere here or here and your classifier will still work. If the margin is small and a new data point appears here, then your classifier does not work so well. So in general, a classifier with more margin is more robust, right, and that is sort of what we would like to find. So the perceptron algorithm does not guarantee that you will find such a thing, but there are other ways, as we will see, which can sort of find you a solution with wider margin.
How do you say larger margin? Can you say
The margin,
margin is way robust?
it is robust simply because you create more gap between positive and negative classes, right. So in some sense you can have more confidence that this is the valid separator. If the margin was smaller, then it is not clear if the separator is robust, is like properly separating negative and positive points, right. And you look at this separator with less margin, right. So new data points could arrive maybe around old data points, right? So a new data point, say, which is appearing a little further away from this, could end up on the other side of the separator, whereas in this case the new data point has to arrive quite far away from all the data points that you have here, right. That is all. I mean, if you go by the idea that the training data set that you have is sort of representative of the general data set you will see when you start using this in the real world or something, right. So then you can estimate that new data points that will show up will be close or nearby the data points in the training set.
So margin is always depends on your data or your procedures.
So the margin of a hyperplane depends on the data and the hyperplane
So not,
and the separator. Yeah.
not in the what is the algorithm we are using. It's not depends on the algorithm.
No. So the algorithm we saw so far, that was the perceptron algorithm, right? And the algorithm there we didn't really use any notion of margin. All we said was positive points should evaluate to positive under some dot product, negative points should evaluate into some negative under that dot product. That's all. We didn't say anything more. So here we are trying to sort of say something more, that positive points and negative points should have wider gap. Okay. So, this is what we wanted in perceptron essentially, right. So, I will say that a vector w, so this time we are back again with this b, but so vector w, like let us just say w to the whole thing. W is a valid linear classifier or a valid perceptron output if it satisfies this thing, that for every positive point in my data set, the dot product of w with that vector is positive, and for every negative point it is negative. Right. So, if this happens, then w is a valid classifier. Right. So, now what you could think of it is sort of like this. So, because you are working in a discrete situation, right, you have a limited number of these things. So, it is not, it is greater than 0, but there will be some minimum value that you get here and some minimum value that you get there, right. So, what we can try to do is sort of scale the values of w's, so that this minimum value increases to 1 and then that other value becomes minus 1, right. So, as I said, so we, I guess in today there was a discussion on these things as well, right. So, or in the yesterday's lecture we saw how we went from w to w star. So, this is that w star essentially. So, now once we have this, we can sort of visualize this thing like that, right. So, here is your classifier, right. So, this is a hyperplane. So, you can describe it by this equation, and these are all the positive points such that w transpose x plus b is at least, it is greater equals 1, and for things certain things it could be exactly equal to 1, right, and for say this point it will be strictly more than 1. And so, the further the point is from the hyperplane, the larger that positive value. Similarly, on that side, for certain things it will be equal to minus 1, and then you further you go away, the more negative that value becomes, right. So, these points in your data set, assuming some exist, such that this dot product evaluates to 1 for them or minus 1 for them. So, these, remember, your data points are some vectors in some vector space, right. So, these points will be called support vectors, okay. And in some sense, if you knew what these points were, you could have defined your linear separator using just these guys, right. But before we go there, let us notice one nice thing, that what does this equation represent when you write this? Sorry?
It's a plane.
Yeah, it is a plane, but okay. So, how is the equation for a hyperplane written? Like, what is the intuition?
From the subspace.
Right. So, okay. So, let me just say it. So, when you write down a hyperplane, right, so you specify it in terms of like some dot product, right. So, what you are saying is that the points that lie on this hyperplane are those for which this dot product is 0. Right. This dot product is 0 in the sense it means that so in the other sense, like the meaning is that these x, so this w is basically a vector which is orthogonal to this, right. So, now if you get 1 for a particular vector, what does it mean?
Every other
No, it means
every other points are orthogonal.
no. So, it means that the distance of this point from this hyperplane is 1.
Yes.
So, the dot product of any point with this equation, like when you substitute that point in this equation, in this dot product, the value that you get is basically the distance from this hyperplane to that. So, there are of course some more conditions on W that I did not speak about, right. So, for example, I guess this has to be a unit vector which is orthogonal to the hyperplane and so on and so forth. But essentially this equation gives you the distance from the hyperplane to that vector. Right. So, what we are sort of trying to say here is that we want to maximize the distance, right, from the hyperplane to any data point, right. And if you scale things by some constant or something, you can bring down that distance to be saying it should be at least 1, right. That is what this is saying essentially. Yeah.
transpose X plus B equal to -1.
Uh-huh.
Some element may not be there, sir. On the
No, so I will scale the values of W so that this happens.
No, I am telling that the W transpose X plus B equal to 1, some point will be there because such way that only W star we define.
Okay.
But the -1 case is
Okay, here is how I do this. So I have, suppose I know that this is one point and that is one of the support vectors, right?
support.
So suppose somehow I know that these are the set of points which will be at distance 1 from the hyperplane, like on the positive side, and those would be at distance something from the negative side, something like this.
Yes.
So what I do is that I will just choose a hyperplane which is midway between them. So at this point, this guys and those guys will be at the same distance. And then I can scale the value so that this becomes 1, that becomes -2. So if you give me one W, I will give you another W which is sort of slightly shifted but parallel to the W you have given me, like parallel to the hyperplane you have given me, and that will have the property that I want. Right. So I am not like doing the math proofs here to, but you get the idea, right? And if you try to write this down formally, you can. So essentially what we are trying to do now as compared to yesterday is that we are trying to find a classifier for which the distance of this classifier, the orthogonal distance of point from this classifier is maximized. I mean the distance of this point from this classifier, that point from that classifier, this thing, right. So the minimum distance among all points, that is maximized. That is the type of classifier we want. So if you maximize this, then the gap between positive and negative points is going to be twice of that, right. So if we can maximize this, then we have maximized the margin between positive and negative points as we wanted, right. I mean as in this picture. So instead of finding that top separator, you will find the bottom separator, the larger margin. So once again the solution may not be unique, or maybe it will be, I do not know, but you will find the one with the largest margin if you like basically can do it properly. Right. So, I mean we have set our objective function to be this, right. So, once you have this as your objective function, so you can write down this program. So, did you guys see linear programs today? So, this is almost like a linear program, except that the objective function is not linear, but it is sort of quadratic. So, this is called a quadratic program, right. And so the format is linear, at least the constraints and all are linear, it is just that the objective function is quadratic. So, now you can have other quadratic programs where these things are also quadratic and so on and so forth, but we do not have that here. So, fortunately this can be solved, right, and essentially the solution will come out in terms of these support vectors. So, the way we solve this is not, I will not cover this, but what you can do is that you can, as in the perceptron algorithm, right. So, if you recall in the perceptron algorithm, the final W that you got, right, it was obtained as by adding the vectors of all these other data points, right. So, it was a linear combination of the vectors of the data points. Similarly, here the solution is once again going to be a linear combination, but of a subset of the data points, in particular of these support vectors, the points that are closest to this hyperplane, right. So, there is some algorithm which will figure out what the support vectors are going to be, right, and then so essentially for every data point. So, if you had n data points, for each of these data points you will figure out these multipliers which will be 0 if they are not support vectors and non-zero if they are support vectors. And if you take the linear combination of these data points, that W is going to be just summation of alpha I x I plus b. Yeah, right. So, the format of the solution is the same as the form that you got in perceptron. In both cases you are getting linear combination, but in this case the what are these, the coefficients of these vectors that compose it, they are going to be obtained in a different manner by solving that quadratic optimization problem.
So why is the objective function is linear is you can take, why sir you are taking the quadratic?
It is quadratic because that is what we wanted, no? We wanted to maximize the margin. So which is what? Which is the distance?
Yes sir, I agree, But I'm telling that it's a finite dimension only. Every norms are equivalent only, master. You can take that.
Every norm is equal.
Equivalent.
Why?
You can find it actually. Every norms you are equivalent with it.
Like minimizing one norm.
One norm
implies-
implies every norms are same only.
I don't know this.
Like instead of, I think.
Is a taxi norm if you are taking that is linear programming problem only with norms.
Right, but here we are using L2 norm, and I don't know why minimizing L2 norm is the same as minimizing L1 norm.
Because that's a theory. It says that you find them so every norms are.
I don't know this, so I am not going to use this. Right? As far as I know, these would become separate problems.
No, the meaning of that is different when you say norms are equivalent.
Yeah. That is basically out of scope for what I am trying to say here. I mean, I also don't think that is true, but I am not going to contradict you right now. All I am trying to say is that we have set up our objective function as a distance as the L2 norm, and so it becomes a quadratic program. If you use some L5 norm, it would become whatever, some other higher degree polynomial program. Right? Up to quadratic programs, there are like algorithms or something that can solve these things, but as the polynomial degree increases, the difficulty also increases, and in some cases it is not solvable. I think even L1 norm becomes unsolvable in certain cases. So, it depends on the structure of the program itself, but whatever. So, whatever we get here in this specific case, this particular program is solvable, and there are efficient ways to solve them, which will give you these coefficients, using which you can write down this W.
So then maybe it is Lagrange multiplier you are using means the differentiability may miss if you are using L1. That is
Mean. I don't. I will not comment on that.
Excuse me, sir.
Yes.
Sir, I just want to ask that thing that perpendicular distance to nearest point vector is 1 by W naught.
Mm-hmm.
Just want to please just clarify this.
So, this is basically because of the scaling we did, right. So, we had some W,
Okay.
right. So, if you turn it into unit vector, what do you get?
1 by W.
Right. And so, you want the minimum distance to be that much, right. So, the
Okay.
so that is all.
Okay. Thank you.
Okay. So, the bottom line is that so finally, when you solve all these things, the solution that you get turns out to be like this, right. You have these coefficients that you get by solving that quadratic program. So, and as I said, whenever this alpha is non-zero, it is a support vector, which is to say it would be one of those points which is like one of these points which are closest to the hyperplane, right. And so, the solution that you get, the hyperplane that you get separating positive and negative, that is a linear combination of the data points. Right. Okay. So, this is what is known as a support vector machine. So, you have the support vectors and they together describe the solution, and so this is called a support vector machine. Right. And this whole thing you have only written down everything in some linear way. Right. So, let us go a little bit further and ask what if there are some errors. So, where is right. So, what if you would like to find a good classifier. So, your data has some errors, as in for whatever reason a point which should have been somewhere here has some error added. So, it moves over here, right. So, now if you try to find out a linear classifier for this data with errors, then you will probably not find the best thing, right, because then you are also trying to fit the errors, which will make your life difficult. So, you will find some solution which has lower margin and so on and so forth. So, what we do is that we extend our quadratic program like this. So, we have this part where we wanted to maximize the margin, right, which like we want to maximize the margin which was 2 over the length of this, which is the same as minimizing this, the converse. And in addition, what we do is that for every data point, like for all the things in the positive side, we say that the distance of the data point from this hyperplane that we want to find should be at least 1 minus some error, which we currently do not know, but some error factor we add. This is also a variable. Similarly, for the negative things also we add this error factor, right. and then in our objective what we want to do is minimize the total amount of error, right. So, this new thing is again a quadratic program which is more complicated, but otherwise it is still solvable. So, once again you can solve it, and at this point you will get some solution where some of these data points, for example, these boxes which were supposed to be there, this actually ends up over here, and that is allowed, right. So, what is assumed is that we will find a separator which separates most of the points with large margin, except for a few which are sort of on the wrong side or maybe too close. So, this makes this classifier even more robust or able to handle errors in the input data. Is there more detail on this, right? So, the solution that you will get, it will be in the same form as before. It will again be a linear combination of things, but yeah, it will be able to handle some amount of error in the input data as well. So, you have handled the, so we have seen how to handle the case of when there is a linear separator, also the case when there is a linear separator with some error in the data. But what we cannot truly handle so far is what happens when the data sets are like this, right. So, they are like completely not separable by any line, no matter how much error you try to pull out of it. But as we saw yesterday, these things can be solved by projecting the data into a higher dimension, right. So, let us go to that part now. So, any questions so far? Any questions for the things that we saw so far? Okay. So, now we come to this case where now we try to work with some amount of nonlinear data, not linearly separable data, sorry. Right. So, the simplest case is that of this circle, right. So, you have positive and negative data points once again. So, the proper way to separate them in 2 dimensions would be this circle, but this is not a linear separator. But what you can do is that you can, if you are smart enough, you will figure out that if I transform my data point x y, I mean here x and y are coordinates, into x, y and x square plus y square, then I get from 2D I went to 3D, and in 3D if I look at the z dimension, then there is a linear separator separating the positive from the negative, right. So, if you wanted a fuller picture, that would have been essentially why don't we, it will be something like this essentially, right. So, this was sort of like negative and positives are sort of in some circle like fashion, right, and when you project it to 3D by using this like x square plus y square, then the things sort of become like this, and at this point you can push a linear separator between them, right. So, in the original 2-dimensional space you could not have fit a linear separator in any way, but once you go to this new 3-dimensional space using some mapping which is denoted by phi over here, then you can, right. So, this was our original support vector machine solution format, right, which was a linear combination of these xi's, and then when you get, so here when you have some new point z to classify, so that can be written, what was this thing, right. So, this was so this thing is, oh sorry I keep getting confused. So, this thing is essentially w dot z plus b, right. So, what is w dot z? Because w is a linear combination of these xi's, alpha xi and so on. So, the dot product expands over this linearity. So, you can just directly write it as the sum of these dot products, right. So, that is what is written here. So, when you go to the higher dimension, then this xi is transformed into this thing, right, this other vector in the higher dimension, same happens with z. So, therefore, the support vector machine or solution that you will find, it will be in this form, So, the way to deal with nonlinear data in this support vector machine system is to basically project it to some higher dimension where they become linearly separable, and then to find the best linear separator, right. So, if you try to basically, so what do we need from this? Any question, something not clear?
Data set doesn't have any linear separable, right?
Yeah, the data set as given does not have any linear separable.
Then how we can able to get the SVM, linear vector?
So, that is what we do. We take the data set which is in 2 dimensions, right.
But you said that we use this thing and then after applying the transformation you get.
So, I take my data which is in 2 dimensions, and I, in this case here, I project it into 3 dimensions, right.
Okay, in order to project that you need that.
So, in order to project this, I need to know this transformation that I have to apply phi. So, in this example, I manually created this phi. So, somehow one way or another, you also need to know this phi. So, you need to know how to project the data into some higher dimension, so that the linear separability thing works. Yeah. So, the trick in support vector machine always is to find out this phi. Right. If you have to somehow figure out what phi to use, and if you use the correct one, then this process will work, right, because by applying phi, linear separability shows up essentially. Okay. There could be many different phis, yeah, it need not be unique.
At all possibilities we can reach optimal solution like separate.
Yes, for every possibility, as long as the possibility gives you a linear separation, you can reach optimal solution. Well, you can reach some solution, not optimal. Now, let us just take this form of the solution a little bit further, right. So, here there is one issue, which is that, well, here we went from 2 dimension to 3 dimension, right, but if you are already working with some 100 dimensional data, maybe you need to project it to some 1000 dimension, or if you are in 1000 dimension, maybe you need to project into some 1,000,000 dimension. So, this process requires the data to be projected to some very large dimension, right, and then you want to solve some quadratic program involving blah blah blah, and then you produce a solution. So, as the number of as the dimension increases, the complexity of solving that quadratic program also becomes more and more like the cost increases more and more, right. So, what would be nice if we could sort of skip doing all that, right, and sort of maybe directly figure out what the value of this particular dot product is going to be. So, if you look at just this part here, so it is what is happening here, we are first mapping every data point into some higher dimension, like so this gives you 2 new vectors of much higher dimension, then taking their dot product, right. This is what is explicitly happening, but maybe we can write down another function which will just directly do that instead of doing all this mapping and dot products, right. So, an equivalent function. So, for that, so suppose that if your mapping was something like this, which is a fairly complicated object, right, then if you write it like, if you start expanding this out, eventually you will arrive at something like this, right. So, therefore, I do not actually need to do this mapping first and then take the dot product. I can, whenever given x and z, I can directly just compute this value. So, this is called a kernel function. Okay. I mean, this method of not projecting, but directly computing this dot product using some smaller function, right, this is called the kernel trick. So, this is the kernel, and this kernel trick is to directly compute this dot product value, right. So, this is denoted by this k, right. So, k denotes the kernel function that you are using for this whatever data set that you are working with. So, this kernel function is something that you have to figure out what it should be, or rather there are some standard kernel functions that people use and it generally works, right. But the point is that once you start using kernel functions, then all those complications in your life sort of go away, things become much simpler, right. So, now everything, yeah, so now you can see that that solution can be written in this form, right. So, that dot product has gone away and just k has shown up, right. So, this is what all you have to do. So, now the question is what is a valid kernel function. So, like there are mathematical, so this particular theorem it specifies why some function k can be a valid kernel function versus what can not be a valid kernel functions. So, there are some conditions on this k. Once you write down k as some in some matrix form over all data points, right, then that matrix should have some nice properties like positive semi definiteness and other things. If those things happen, then this k that you have chosen, that is a valid kernel function. Yeah. So, if your training data set was x1 to xn, then you can write down this matrix which is called the Gram matrix, where in this coordinate it would be the kernel function between this x1 whatever xi and xj. Right. Yeah. So, here are some choices for these kernel functions. Like polynomial kernel means that you just take the actual dot product between these two things, add 1 or whatever, and then raise it to some kth power. Right. Another would be this exponential kernel function, which has this form. Essentially, what we do is that we try to interpret this kernel function as some sort of a similarity measure between the points, right? And just by using this notion, we are able to basically figure out like a proper classifier for the data. Right. So, in particular, it turns out that this particular kernel function works for like most kind of data sets. If there is going to be some projection for the data such that it will become linearly separable, then it is very likely that this will actually work. And there are multiple choices, but this particular kernel would also most likely work. Right. So, this is one of the most popular ones that people use. Okay, the slides end here. Right. Right, so these slides do not have any proofs of anything. So, I mean this was for our data science program, where we focus more on the like how to use these things part rather than the proof part. But yeah. Okay, so any questions about all these things?
Similarity, like you call that function as a similarity measure. Is there any name, meaning, is there any proper definition of similarity measure function, or?
So, you have this data points, no? So, I want to say how similar this data point is to that data point. That's all. So, k like it is a function, similarity measure, or you can, if you want to be formal, you can think of it as a distance function between this data point and that data point. That is another data point.
Yeah, but essentially this does not give the distance or any other.
No, this is not the L2 distance, this is a new distance function.
Yes.
So, that is why I am calling it similarity and not distance, not to confuse it. But it is some similarity measure essentially. So, okay, so let me just say that before neural networks and other things became prominent, this support vector machines were the most popular thing that people used to do. And the way research worked in this area was that people would come up with more and more clever kernel functions, right. So, if you want to recognize some pictures, classify some photographs or something, somebody would come up with some very clever and complicated kernel function and show that, well, this new kernel function improves performance by 5%, things like that. Right. So, the difference now in this neural networks is that you do not have to manually construct the kernel function. The neural networks sort of do that automatically. So, as I was saying yesterday, neural networks also do a sequence of transformations, and at the end it is once again a linear classification solving problem. Right. So, support vector machines are also solving a linear classification. So, they sort of transform the data in one step in some sense into a new, like from one format to another format, where here you get linear separation, and this transformation is figured out by humans. Right. And now these neural networks, they learn this thing via this gradient descent training, and they are able to basically come up with good functions which accomplish the same thing in some sense. Yeah. So, Sorry.
Can we see Ji in this geometry?
Jai is basically the. This is what it is written here. No?
So can we see geometry relate
I don't understand what do you mean by see it in geometry.
Ji?
The square point which is laying here in the other positive side.
Yes.
So with the other support machine, we'll create that Xia.
See, look at this.
XA has the
So
XA
you
is
take
here.
this point, you take the dot product of this point with the unit vector orthogonal to this guy. That will give you the distance from here to here.
Yeah.
So because it is supposed to be on that side, it should have been whatever 1 or minus 1.
Plus that.
But it is over here, so you get something else essentially. So that xi is added or subtracted as per the. It is just the error in the distance. It should have been 1 or more, but it is actually in the opposite direction, so you have that. It's just the error in the distance between the point and where it was supposed to be. There's nothing else to it.
Sir, our objective function is not differentiable. Then how you are applying the Lagrange multiplier methods?
I don't know. Like I said, I am not discussing the algorithm. I am just saying this is a quadratic program and it can be solved.
No, sir, the previous slides you are seeing Lagrange multiplier.
Okay, previous slide, to open previous slides. Yeah, I'm not discussing here how we find this. I'm just saying there are standard algorithms or standard methods to find this.
Next slide you are using Lagrange expression, you
Correct.
apply a Lagrange multiplier method.
Yes.
So that time objective function you are take norm square only you have to take as usual.
Yes, but as I am saying once again, I am not describing how this is being found. I am not describing the algorithm. So even if it is not differentiable, maybe you can approximate it by a differentiable function. And
No, so
work with
usually
that.
they will take the
Awesome.
square, they will take, sir, norm square they will take.
Yeah, so there are many other methods of solving this even if the objective function is not directly differentiable. Right? So you relax the certain things, you can approximate it by a different function which is differentiable, things like that. But all of those things I am not going to discuss here. So I mean that goes into how you solve some convex quadratic programs or something. That is not in scope here. My objective here was to show how you basically find how you separate how you construct classifiers using the basis of which is just simple linear algebra. So because we have some time, let me go over one other topic a little bit quickly. Oh, maybe it's not here. Okay, so let me just try to sort of do it. By where isn't it add any page? Okay. So one of the things that we saw was that at least for support vector machines, you have some data in some dimension, and normally you want to project it to some higher dimension to get this linear separability, right. So all of this is fine when essentially you want to find these type of linear separators between data, right. But then there are these other type of machine learning algorithms, for example clustering, right. So where the idea is that once again you have some data which is represented as vector in some vector space, right. No, I should use some other thing. Right, and what you should do is essentially figure out that this should be one cluster, that should be one cluster, this should be another cluster, and that should be another cluster. Right. So in clustering, the key thing is it's all based around distances between pairs of points. Right. A bunch of points which are close to each other should lie in the same cluster, and a bunch of points which are far from each other should probably lie in different clusters. And then there are many other considerations here as well. So once you start going by distance, other kinds of problems shows up. But one of the key things is that it is all based around distance, right. So, now let us say I have a bunch of documents, maybe a bunch of news articles or maybe research papers or something, right. So, as we saw in the first lecture that there are many ways to convert these things into vectors. One way would be that you think of it as a sequence of words and then you encode each word as some vector, right. So, even then whatever you get, the final document itself would be a very, very long vector, right, very high dimension. So, the problem with high dimension is that finding distances and doing any of these things, it is expensive, right. So, when you are trying to do some sort of clustering, things which are just based around distances, then you can do some other things. One of the things that you can do is that if you had, no, this should work here. If you had some data points which are x1, x2 up to xn, right. So, these are some vectors in some, let us say r raised to l, some L dimensional space where L is very large. One of the things you can do is that you can take a matrix, a random matrix A, which is some L times let us say 100 log n. Here n is the number of data points you have, right, and then you look at the following collection of data points, which would be, let me write x1 prime, x2 prime, xn prime, where xi prime is equal to a times xi. Did I get the dimension correct or should it be the other way around? This is okay? Can anyone check if it should be a times xi or should it be xi times a? Okay, I will leave you guys to fix this.
Excited. Okay.
So, my point is simply this: if you have a bunch of very high dimensional points, then if you do a random projection of these points, like by which I mean that you take a random matrix and multiply each point by that random matrix, right. Then and let us assume that like the norm, some L2 norm or something of this matrix is 1 or something like that, right. Then these are the new points that you get, and the pairwise distances between these any two points here is roughly going to be the same as pairwise distances between any two points there, right. So, I did not state this formally, but formally this is basically a version of this Johnson-Lindenstrass lemma, which says that if you project a bunch of points, like if you project a set of vectors, set of n vectors to some order log n dimension, then you are going to preserve the distances approximately, right. And this is sufficient for our clustering, which is just based on pairwise distances, right. So, instead of doing our clustering in that high dimension, I can do it in this much smaller dimension, which is just say 100 log n, and this would give you almost the clustering would give you the same results that you would have gotten in the higher dimension, right. So, as far as machine learning is concerned, both increasing the dimension and decreasing the dimension, both of these techniques are used, right. So, this is one method. Some other things that we will, I do not know if PCA or something has been covered, right, singular value decomposition, all these things. So, those are other methods of reducing the dimension of the data while preserving the main properties that you need, right, depending on context. So, here for example, if I was looking for some linear separability or blah blah blah, that is definitely lost, right. So, I cannot find some linear classifier, things like that in this new set, right. But the pairwise distances would be preserved, and that is what I needed for clustering.
Any specialty of log n or any kind of function?
No, so people are interested in like how small this dimension could be, right. So, this log n turned out to be the lower bound. If you go any further below, it will not
Yeah,
work.
it's very affiliated.
Okay, so then let us stop here. We still have a few minutes, but yeah. So any questions from the discussion today, for example, which I think was based around perceptrons?
Second question.
What was the second question?
Prove that if the positive and negative points are not linearly separable, then perceptron's algorithm does not terminate.
Correct.
So after transforming them to linearly separable.
Yeah, so if the points are not linearly separable, then
Then
what does the algorithm do, right? I mean, the algorithm by definition terminates only when there is a linear separator. Right? If the positive negative points are not linearly separable, it cannot terminate. I mean, it was not really, it will just loop forever, right? Because there will always be some point which is wrongly classified. Because if every point was correctly classified, you have found a linear classifier. But that violates the assumption. So did you guys try out some example runs of the perceptron algorithm?
some basic example.
No, that will just give you a good idea of what it is. Okay, so tomorrow we will cover maybe some other things based around
Sir,
these.
please share the note with us.
Huh?
Please, slides notes with us.
Yeah, I shared it with Amrita.
Okay, we have not received. Okay, we'll link.
We can. You search for Madhavan and DMF. This is a course that is taught at CMP. Search for Madhavan Mukund and data mining and machine learning. You should get the lecture.
So, there will be